All right. So we want to look at sum check over the product of two multilinear polynomials. Okay. So I've ever give like why we're learning all these tools in the first place. Yeah, GKR. But like where does it fit into the GKR polynomial itself? Mm-hmm. Mm-hmm. Okay. So we want to run sum check over that FBC polynomial. The problem right now is that our sum check cannot run over that polynomial. That polynomial is too complicated for our current version of sum check. So the idea is like wi of r, right, is equal to the sum of right? Right? This makes sense, right? So we can't run sum check on this right now. Like what your sum check runs on is, it runs on a polynomial in evaluation form, right? Just evaluation form. Right now we have this that is composed of multiple polynomials in each of them having their own evaluation form, right? Like the add I has its own evaluation form, mul I has its own evaluation form, then wi plus 1 also has its own evaluation form. So what you could do technically is that you could multiply all those evaluation forms, add them up until you get just one. But this polynomial is not multilinear, right? It's multivariate. It's quadratic. It's not multilinear. So that to represent that polynomial in evaluation form, you need to walk over 3HC. Yes. you need to walk over 3HC. So it's not going to be in terms of just like 0, 1. It's going to be in terms of 0, 1, 2, right? Because it's going to be a quadratic. But then what we're talking about now is that it's more expensive to go to that HC than to just stay in the multilinear scenario. So let's assume that we had two polynomials. Now we're just talking about multilinear polynomials now, okay? So let's say we had f of a times f of b, right? F of a has how many evaluations? 2, right? Single variable. F of a. And f of b has how many? Now if we multiply two of them together, we'll have gotten sorry. Let's do something else. Let's do f of a times f of a, right? I want it to be non-multilinear when we multiply. Does it make sense? That was the f of AB. To be more interesting this way. So this will have how many now? And this one will have how many? At the end of the day, we're going to get it's the same polynomial f of AB, right? But this one is now quadratic. Okay? So that means we're going to do it over 0, 1, 2. Right? I'm trying to verify if this is actually more expensive. So this will be like 0, 0, 0, 1, 0, 2, right? 1, 0, 1, 1, 1, 2, and then 2, 0, 2, 1, 2, 2. So now this has like 9 points, right? While this other one has 8 points. To get this 9, that's like 3 to the power of 2. You know, the base now is 3. Why to get this one, it was 2 to the power of 2, 2 to the power of 2. So it's always like the base raised to the power of the number of variables. Now let's assume we had 3, in this case, A, B, C. And we also had A, B, C. This will be 8, right? Yeah. And this will be 8. Then this other one will be 3 to the power of what? 3. Which is what? So we're going to use 16 memory slots for if we store them, leave them in their multilinear form. But then we compress them down to their multivariate form. We're using 27 now, right? Let's assume it was 4 now. So it will be 2 to the 4. 2 to the 4. That's what? 16, 16, right? That's 32. It will leave them multilinear. What is 3 to the 4? They say that the gap is getting wider and wider. So that it makes sense sometimes to leave it like directly in multilinear. That polynomial library I was talking about that is able to move in between can now decide whether it wants to keep it in multilinear or merge them into a single evaluation form. So sometimes it makes sense, sometimes it doesn't make sense. Like in this case where it was like 8 compared with 9, it's not really that different, right? But then once it starts getting bigger, then you now start seeing like some crazy space. So now I want to look at running Sumcheck on when you keep them multilinear. Like how would that look like? So let's use the example we've been using so far. That's 2ab times 3ab, right? That's 6a, no, times. It's product of two multilinear polynomials. Okay? So you have one multilinear polynomial. Like if you're adding two multilinear polynomials, it will still be multilinear. Like the power will never increase when you're doing addition. But if you're multiplying two, that's when you can get into that case. Let's run some check on this. Regular old sum check. Okay? How many variables? 2 variables, right? Cool? Yeah. What's the sum over the Boolean hypercube? We evaluate at 0, 0, right? What's 0, 0? 0, 1? 1, 0? So this is the sum, right? The prover is supposed to send that to the verifier. But the prover is also supposed to send the f of a, right?
So how are you evaluating over Boolean?
No, it doesn't have to be. So the way Sumcheck works is that Sumcheck proves that if you sum over a domain, the sum is equal to something, right? So you can literally use any domain.
Because I don't think this is sufficient enough. Because if we still do 6 8, it's still going to give us this.
Yes, but it's fine because of, how do I put it? The main idea of Sumcheck is you put your data somewhere, right? You put your data in a structure. So you could have put your data in the 6ab structure, or you could have put it in the 6a squared b squared structure. What's important is that you know where your data started from, and you know where your data ended at, right? Now in GKR, we never put our data in the 3HC space. Do you get? Like, we're always working with multilinear polynomials. So all the data that is relevant to GKR is in 0, 1, is in the Boolean hypercube. And then Sumcheck is attesting something about the data that you have put already. So if you're now trying to do Sumcheck over 0, 1, 2, you're now including data that you never put there in the first place. Does that make sense? But you could have, in your GKR, decided that, okay, I wanted to start with 3HC directly. Then when you're running Sumcheck, you run it over 3HC. And actually, that might make your GKR easier. That's all, if someone is ambitious enough, someone should experiment with that. So rather than working in Boolean hypercube, you work in 3HC, in quadratic polynomials. So rather than using multilinear polynomials, you use quadratic polynomials. So all your W's will all be quadratic polynomials. That way you will never have to do any of this like product and everything. But does the current sum make sense? Hmm? Project? Oh, project of it. Yeah. So our data is in Boolean because we use multilinear all the while. So when we're doing Sumcheck, we'll also do Sumcheck in Boolean. Okay? Now, let's get the f of a polynomial. To get the f of a polynomial, we're going to skip a and sum b over the Boolean hypercube, right? So that's going to be f of a0 plus f of a1, right? So this is what? 0 plus what? 6a squared. Make sense? So our f of a polynomial is cool. Now this is a quadratic polynomial, right? So before, you have always been getting univariate polynomial. You have always been getting like straight lines. That's degree 1 polynomials as your round poly, right? That's why you have only been sending 2 points. Does that make sense? Yeah. 0 and 1. But now it's a quadratic polynomial. 2 points are no longer enough to represent this, right? So you're supposed to send 0, 1, and 2. 3 points for a degree 2 polynomial. So what is the verifier? What is the prover going to say to verifier? You're going to send the claim sum, and it's going to send the polynomial. Let's assume we're sending it in evaluation form. Okay? So evaluation at 0 is what? Evaluation at 1 is what? Evaluation at 2 is what? So this is the same polynomial, right? If I interpolate 0, 6, and I get 6x squared, which is the same thing as 6a squared. If you had dropped one of those points, let's say you just did the regular 0, 1, you'll have gotten 6x, which is no longer the same round poly, right? This is why it's necessary to evaluate at 3 points.
So what we are doing basically is we are summing over the Boolean hypercube for the quadratic polynomial. But if you want to send the polynomial itself,
The round poly.
you send it as a 3AC polynomial.
You send it as a, so like every degree d polynomial is representable in d plus 1 point. So that's a degree 2 polynomial. So to send it, you have to send 3 points.
3 points.
Yeah. Even though you're not sending the same polynomial again. If we're working in coefficient form, both the prover and the verifier working in coefficient form, it will send the 6a squared just written like that.
Yeah.
But then if you're working in evaluation form, you need to make sure that you send the 3.
And the evaluation form of that polynomial, we're evaluating at
0, 1, 2.
and 2. That is 3AC.
That's 3HC. But you could also have evaluated it at 4, 5, and 6. The point is that you have 3 points that are on that polynomial. And the verifier knows how to interpolate it back to get the original round poly. The only goal is that you want to send that 6a squared polynomial to the verifier, because the verifier needs it to get the next claim sum.
What's the generic of
The generic of this is just send d plus 1 points that are on that polynomial.
Can we compute d plus 1 point to get this polynomial?
I mean another set of points?
No, like this 6a squared.
Yeah.
D plus 1 point.
Just evaluate at 3 points. 0, 1, 2.
Okay. Yeah,
It's just univariate.
yeah.
It's just like coefficient form and point form. Yeah. But now because we don't want to send too much info, because if we had evaluated as something other than 0, 1, 2, we'll have needed to put the x, comma y, right? Because the verifier needs to know where to interpolate. But this is now convention, that the first one is always at 0, second one is always at 1, and third one is always at 2. That way we can omit it. Make sense? So we need to keep track of this because we're not going to do the same thing over now the product. I need to make sure that the prover sends exactly the same thing. Because if the prover is not sending exactly the same thing in both cases, then your transcript would now produce different, which is not supposed to. Okay? Like whether we're working with it in like the full multivariate form or working with it in the product of multilinear, we're supposed to get exactly the same messages between the prover and the verifier. Alright. So now the verifier is going to evaluate this polynomial at 0 and 1. Still Boolean hypercube. So the sum check is done over the Boolean hypercube. But then round polys are sent over the round polys degree. Like you just want to send the same thing. But our entire sum check is done over Boolean. Yes. But if if you're ambitious and you want to do the other one, then it's now be over 3HC.
What advantage does that give?
That's what you find out. You try it and you find out. But the advantage it gives is that all this, what we're doing right now is like we're jumping hoops. If you were already working in 3HC, everything is just straight. It's natural because we are working in the natural domain of that FBC polynomial. That FBC polynomial is a 3HC polynomial. So if you're already working with 3HC, then you can just do element wise and then you get your full 3HC polynomial. We had the idea to try, but we have not tried it yet. But if someone wants to do it. Okay. Exactly that way, yeah. The round poly is hard. You need to know what the power of the round poly is so that you know how many you need to send. Does that make sense? Alright, let's continue. So the verifier is going to evaluate it at 0 and 1, right? And make sure that it's equal to the claimed sum. Evaluation at 0 is 0, right? Evaluation at 1 is 6, right? 6 is equal to 6. Round check has passed. Verifier is going to sample a random R. Let's say R is equal to 2, right? The verifier is going to get the next claimed sum by evaluating this round poly at 2. Does that make sense? Yeah. The round poly is 6a squared, right? Evaluating it at 2 is what? Sorry, let's not use 2. Let's use something like 4. Evaluating at 4 is what? 96. Right? Right?
72.
So this is supposed to be the next claimed sum.
Yeah.
Cool? Verifier sends R. R is what? Right? What does the prover do with this R? The initial poly at R, right? What was the initial poly?
After you found the sum,
Yeah. Yeah. So 6 times 4 squared times what? B squared, right?
Yeah.
What's this? 96. These are what? F of B
Yeah.
polynomial. Now we're sending f of B polynomial back to the So we can send it as either, let's send the evaluation form. I write it at 0, I write it at 1, I write it at 2. One nine two. Why is why are we getting different answers?
384.
384.
That's 6 plus 4.
Yeah. 384. That's it, right?
Yeah.
What does the verifier do? Evaluate at 0 and 1, right? That's 0 plus 96. And ensure that it's equal to the last claimed sum. It is, right? Then he now samples a random challenge R. Let's say R is equal to 5 this time.
Those 3 points that you test is represent 6a squared.
Yes.
Did you just
0, 1, 2.
okay 0 1 2?
So R is 5 now.
Sorry, I missed the point where you said why we need to use that 3 points. Is it because
Because the round polys are quadratic.
okay,
So degree 2.
makes sense.
You represent a degree 2 polynomial with degree d plus 1 point. Okay, so what's next now? Oracle check, right?
Yeah.
So that was the last. So the verifier gets the expected oracle check results by evaluating this polynomial, right? At 5. So that's like 96 times 5 what? Square, right? That's what? That's 2,400. Then we evaluate the initial at what? Which is 4 and 5, right? So we evaluate like 6, 4 square, 5 square. We already know that this will give us 96, right?
Yeah.
And then 96 times 25 will give us. So this is the end. So let's see the messages that we sent. We sent 6, and then we sent 0, 6, 2, 4, right? That goes into the transcript. Then we squeeze from the transcript 4, right? Then we sent that goes into the transcript. And then we squeezed, right? And then that's all. So these are the prover verifier.
That point where prover sends the first polynomial. What did the verifier do? So the verifier was supposed to evaluate that polynomial at 0 1.
Yeah, no, 0, 1. We're working over the Boolean hypercube for Sumcheck. We're working over the Boolean hypercube for Sumcheck. That's the round poly. The 0, 1, 2 is just to communicate the same round poly. Because if you drop 2, the round poly was 6a squared. If you drop that 2, it's not 6a squared that will go to the other side. It's going to be another poly. Because that's a quadratic poly. It needs 3 points to be able to sufficiently uniquely identify.
Evaluating it at 0 and 1 is still sufficient enough to just say I'm proving it.
Wait, yes, but the next claimed sum. Like if I went at just 0 and 1, it will be 6a instead of 6a squared. Now the verifier sampled r equals 4, right? If you do 6a at 4, that's what? 24. If you do 6a squared at 4, that's like 6 times 16, which is 96. So the claimed sum will not match. Do you get? You need to get fully. It's come over time. Now let's do the same thing. But right now using the 6a squared b squared, which is like the 3hc univariate, let's now do it with keeping the 2. Okay? Side by side. So now, there's a very easy way to think about this thing. Just create the function signature as a black box. So that 6a squared b squared is 2ab times 3ab, right? All you do is just assume that it's still ab, right? It's just that this is not a black box. You can just imagine it's a black box. You already know how to evaluate this black box polynomial. So this is what you have. Sumcheck process is exactly the same. How do we get our claimed sum? We evaluate this polynomial over the Boolean hypercube, right? Which is just f of 0, 0 plus f of 0, 1 plus f of exactly the same thing we did last time.
So that means if we are doing it like this, we are still using our Sumcheck way.
Exactly.
So we don't need to put that.
What you could do is that you could create a. You guys are not going on.
We know.
You could create a product poly, right? A struct that holds a vec of multilinear polynomials. But in that poly, you will still implement partial evaluate and evaluate, and maybe two bytes. Like it will look exactly the way your multilinear looks like. So Sumcheck has been calling methods, right? Sumcheck will just call methods on your product poly now, instead of calling methods on your multilinear poly. But it's exactly the same thing. We'll do it internally. No, just say that if you call evaluate on the product poly, it will evaluate each of the multilinears in its vector, and then multiply them together.
If you want to perform some check on that
Product poly.
what are you doing?
You are still doing your regular sum check.
Yes.
But whenever the sum check calls like partial evaluate A at R, it's not going to partial evaluate each of the ones inside, and then just remains like that. And if it says oracle check, right, fully evaluate, it's not take that ABC that you're passing in and go and pass it into each of them, and then multiply the results. Yeah. So you can like
So is this the modification you're talking about?
Is this the what?
Is this the modification you're talking about?
It's not complete,
It's not complete.
but you're close. It's not complete.
But since we agreed that working with multilinear saves us memory instead of so we can do it.
Yes, this is what you should go with. So let's finish it first, right? So now this is like what Sumcheck is calling, right? So to evaluate 0, 0, it means that you evaluate this one as 0, 0, and also evaluate this one as 0, 0, right? So that will be 0 times 0. This one 0, 1, 0, 1, right? 0, 1 on this is what? Huh? Or 0, right? Now this one will be what? 2, 3. This is exactly the same thing we had for the other one. It's just that how we got it was different. But that's a detail that can be hidden behind a structure. Sumcheck doesn't need to care about this. Sumcheck just takes something that has those traits, yeah?
Why? I thought you're not supposed to multiply it here.
No. So when you... So it's like you have a polynomial, right? That is made up of two other polynomials. Or let's say 3 other polynomials. Right? Now when someone tells you that you should evaluate this polynomial at somewhere, what you do is that you evaluate each of them at that place, then multiply it. That's evaluation. It will give you the same result as if you had like fully multiplied them and then evaluated them at
Well, we are
once.
multiplying the final result 2 times 2.
So each of them, so like 0, 0, that's A, that's B. Then 0, 0, 0, 0, 3, 6. So it's exactly the same thing as this one. But this one we already got it by first of all fully multiplying. So now we have something that is in 3HC. Does that make sense? Yeah.
Slow down. If we need the claim sum, right? You know, the way you're representing it now is it's like messing up
What's
my,
problem?
my logic of my implementation logic. So I think, are we getting the polynomial of the product or we just want the claim sum of both of them.
I
Because
mean, here now,
so if you want the claim sum of both of them, it's simply summing this one, multiply the value you get from each of them. But if we need the polynomial of the product, that's when we have to start summing them individually.
okay, so
Like multiplying them individually to get 0, 0, 0, 0.
let me show you what you're saying now.
Yeah.
You're saying we have two polynomials, right?
Yes.
So let's say we had something like this, right? Over the Boolean hypercube, it was A, B, C, D, right? For the first one. Then the second one was what? E, F, G, H, right?
Yeah.
So what I just did now was I multiplied, right? So it's now like AE, right? BF, CG, DH. Then I summed AE plus BF plus CG plus DH, right? This is my claim sum. Now what you're suggesting is you add first.
Yes.
So that will be A plus B plus C plus D, right? Times E plus F plus G plus H. Then you multiply. That will be AE plus AF plus AG plus AH plus BE plus BF plus BG plus. You see, it's not. So it's not the same. It's not the same. Come. Why?
What you're doing here now, you're representing this thing. What I'm saying is, it's sum now. If you already get the sum, which is a value, and you get the sum, which is a value.
What I'm telling you now is that they're not going to.
give you.
It's not the same.
So you know why it cannot be the same? It becomes something distribution. So addition is not distributed over multiplication. Do you get that?
It's correct, of course. Of course. But the main idea you should think about is that if your value is 0, 0, you need to do the full thing. And like evaluate both of them, then multiply. That's the way this one will behave the same way with the other one. You get? So when we do the multiplication, we now get like 6. Okay. So now we have the same claim sum, right? Next thing is to get the f of a polynomial. Okay? So to get the f of a polynomial, we need to partially evaluate what? B at 0 and at 1, right? Exactly the same thing. We're saying that f of a is equal to f of what? A, comma 0 plus f of a, comma 1. This is what Sumcheck sees. But then this f polynomial, Sumcheck doesn't know that it's a product poly. It will now go internally and figure out how it will answer a, comma 0. So internally, what is it going to do? It's going to say evaluating a, comma 0 is the same thing as evaluating each of them at a, comma 0. Right?
So how do we define our polynomial in the when we are implementing of it? How do we define it?
You didn't say it on there.
It's a vec of multilinear polynomial.
No, I'm still having issues with that first.
Okay.
I'm still having issues with the Sumcheck.
Which Sumcheck? The first one.
Yeah, the one you did before.
What's the issue?
So now when the require sample the random challenge, first,
4.
yes, and it gives it to the prover. So the prover evaluates
A.
of A
That's 4.
at 4.
They evaluate f of ab, partially evaluates that initial poly at a equals 4.
Well,
Are you forgot Sumcheck? Let's say you had f of abc, right? You send the claimed sum and you send f of a. F of A, you skip the first variable and you sum the rest over the Boolean hypercube, right? So you send the claim sum and send F of A. Verifier will sample R, send it back to you. Then you partially evaluate the initial poly, F of A, B, C, as A equals R. To leave F of B, C. And then continue like that. That is exactly the same thing here.
So what we did was we first evaluated at A.
Yeah.
Then
We now had B, C, just B.
yeah.
And then we'll send that one. Alright, let's continue. So we need to figure out what F of A0 is. Right? 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 So B is 0. F of A is 0. So for this one now, we'll do both individually. Yes, A0, A0. So like your vec of multilinear polynomials. If you ever evaluate the first one, partially evaluate B equals 0, partially evaluate B equals 1. And then you have like two new smaller polynomials. So when you do for the first one, this is going to be like this will be 0, right? And this other one too will be 0. So this entire thing is just 0. Which was exactly the same thing that we had. Make sense?
Yes.
But you say vec of multilinear polynomial.
Yes. So this thing that we're looking at here now, we can think of it as like, what was it again? I'm still working in equation form. Yeah.
So, vec of multilinear polynomial. How do you determine the number of vectors that will be in the vec?
When you're creating a polynomial, you just push.
So, there is here now in the vec, this one will be a vec
Of two multilinear polynomials.
multilinear
So
polynomial.
like you were multiplying the two multilinear polynomials, but you didn't want to multiply it all the way through.
At what would it get more than 2?
For GKR, no.
I-
For GKR, no. But this, whatever we're talking about now, extends to as many as possible. Cool?
But it's 2
For GKR.
for GKR
Yes. The 2 is basically the mol.
of those
So you can see this is a multilinear polynomial.
and this other one.
Then times, at the end of the day, you're going to merge these two into just one,
Yeah.
right? It's going to be wi plus 1 of b, comma c. So this is like another multilinear polynomial. So those two, you put them in one vec.
Okay, the reason why I'm asking, so I just go those vec of 2 multilinear polynomials.
That's for GKR, but I'm teaching you a general method
So if you are implementing, we should implement the generic.
if you want, but it's advice, yes.
Eh?
Yes, you should implement generic. Why are you running away from generic?
I'm just
Yeah, you should implement generic. Make sense? Okay, so now the next one, A1, right? We evaluate the first vec at, yeah, yeah, yeah. I must find them. The product poly. Alright, so A1 now. Okay? Evaluate the first one at b equals 1. That's what? 2a, right? And then evaluate the second one at b equals 1. That's 3a also, right? So that'll be 2a times 3a, right? That's what? So times our f of a polynomial is 6a squared. Which is exactly the same thing as the previous one. But we don't even need to. We don't want the a squared, exactly. So we'll leave it as 2a. Does it make sense? Or cool? So, cool? So now, we want to send this polynomial over to the verifier.
Sorry. one question.
Yeah.
I trying to tell me that if you send this value as it is, right, with the vec form, and you send the times product.
It's 6A.
Yeah, and you send the 6a square.
Yeah. Like you got this.
I think it's probably. Would you get the same
Yes.
value
Yes.
from the transcript?
Yes. So we're not going to send. No. Yeah. We're not done. We're not done. So what's the degree? So I want to ask you guys now. If you have a product poly,
Yeah.
how can you know the degree?
Adding
Number of elements in the vec.
Yeah.
Do you get? So it's like now this vector here is degree 2.
Yeah.
Does it make sense?
Yes.
It's like you have something that is multilinear, there's something that is multilinear. If you multiply two of them, you're going to have something that is in 2 variables.
Yeah.
If you had 3 multilinears, then you're going to have something that will be in 3 variables.
Yeah.
So the number of elements in the product poly is the same thing as the degree.
Yeah, sure.
Does that make sense?
Yeah.
So what before you send your round poly, you ask that your product poly,
Right.
what is your degree? It will tell you that my degree is 2. Then you now say, okay, before I can send you to the verifier, I need to evaluate you at 3 points. So now it says that his degree is 2, we have to evaluate at 3 points. 0, 1, and 2. So if you evaluate at 0, that will be 2A first, right? That's 0.
Yeah.
Then 0. Then we'll multiply two of them, right? So that's going to be what? 0. Evaluate at 1, 2A is what? 2. 3 is what? 3. That's 6.
Yeah.
Evaluate at 2, 2 is what? 4. And 3 is what?
This is what you're still sending to transcript.
Exactly.
I get it.
And 3 is what? 6. 6 times 4 is 24.
Yeah.
Does it make sense?
Does that make sense?
That
Yeah.
means
Yeah.
evaluate are we using
You are using product police evaluate.
product poly as its own.
Yes. And evaluate is like calling evaluate on all the individual multilinear polys and then multiplying all their answers together.
So,
You're getting it now. So you guys will need to create a new polynomial called a product poly. The product poly is instantiated with multilinear polynomials, all of the same variable length. Right? It has to be BC, BC, because you know if you're evaluating the product poly, you have to evaluate all of them.
Yeah.
So they all have to be uniform. If you are partially evaluating the product poly, you have to partially evaluate all of them. Does that make sense?
Yeah.
Let's finish this, then we'll look at it like an implementation design. Okay? Which time? Time day. Time is like mad.
So,
What don't you understand?
Everything.
Is it the sum check you don't understand? Like, do you understand the first sum check? Which sum check? For the first one or the second one? We have done 2 sum checks, right? We're in the process of doing the second sum check. The first one was on the multivariate polynomial, 6a squared b squared. Do you understand that one? I cannot go back to that one because of time, right? So for that one, or let's just breeze through. I'm not rewriting anything. So this 6a squared b squared, right? We want to run some check on this. In order to run some check on this, obviously we need the claimed sum, right? In GKR, you always already have the claimed sum. You guys are seeing why you already have the claimed sum now, right? Like it's W1 of R that's the claimed sum. They are expressing that claimed sum as. So that's why I was saying that your prover is not supposed to be computing the claimed sum, because most of the time it's going to be given to you already. Make sense? So now we don't know the claimed sum, so we're computing it. This is regular polynomial evaluation, right? Because we have this 6a squared b squared, right? 0 for a, 0 for b, and all like that. So that's the 6. Now the next thing is that the program needs to send the f of a. Skip a, sum b over the Boolean hypercube, right? So that means that we need to skip a, 0, plus skip a, 1, right? That's what we're summing b over the Boolean hypercube. Now this one we can never evaluate it straight away, right? A is 0, A is a, b is 0, then a is a, b is 1. That's 0 and that's 6a squared. Make sense? So when you add everything up, you have 6a squared. That's f of a. Now you're supposed to send this polynomial to the verifier, but this is no longer a line. This is now a quadratic curve. And if it was a cubic curve, you're sending 4 points. So depending on the degree of the round poly, that will determine how many points you will need to send. The degree here is 2, so we need to send 3 points, d plus 1, right? So we evaluate it at any 3 random points. But for convention, we use 0, 1, 2, right? Or 0, 1, 2, 3. We just start with 0. Because if you don't do that, then the verifier needs to know what x it is. So you need to now pass it as points, which is now like more information that you're passing over. So convention allows us to make the proof size smaller, okay? So evaluate at 0, evaluate at 1, evaluate at 2. That's 0, 6, 24. Cool?
Yeah.
Now, verifier gets that. This entire Sumcheck has been over the Boolean hypercube, right? So the round poly check is also over the Boolean hypercube, okay? So if you write that 0, that's 0. If you write at 1, that's 6. You sum it up, is it equal to the claimed sum?
Yeah.
It is. Now you need to get the next claimed sum for the next round, right? That's the same thing as evaluating this poly that was given to you at R, right? So it samples R equals 4, and when you evaluate it, you get what? 96. So that's going to be the claimed sum for the next round. Just pause me when, like, there was a place that you didn't understand something, so let me know when we get there. So that's the claimed sum for the next round, right?
That linear deposit stuff that we used to do won't work. So we have to
No.
directly evaluate.
Yes. So what you usually you're supposed to do, you're not supposed to use your univariate poly. Okay? Now that it's not always not guaranteed to be a straight line anymore. You already have univariate poly, and your univariate poly already implements interpolate. So what you can just use is just use your univariate poly dot interpolate, then the round poly, whatever round poly was given to you.
So the univariate poly will now use to interpolate
Yeah, it's to interpolate the points that were given to you.
this 0, 6, 24.
Now give us the polynomial.
If you give us the
Now
univariate
just
polynomial,
evaluate.
you now evaluate that at R. Do you understand? Huh?
That no more work.
Wait,
It
this,
does not have to has been
why are we
used.
giving the univariate poly this guy?
Because it's not
This is,
Polynomial.
wait,
Like at some point in time, right, the verifier needs to evaluate this round poly at R to get the next claimed sum. Before it was always a line, so you were using that y1,
yes,
yes, but now it's not guaranteed to be a line anymore.
okay.
So like that y1 blah blah blah, your univariate poly could have done it also. Your univariate interpolate. It's just that writing it as y1 plus is faster than doing Lagrange. Do you understand? So what you could do is that another thing you could do is that instead of the prover sending the 0, 6, 24, the prover could send the univariate poly, like directly. And the prover will do the interpolation on its own end and then send you the univariate poly.
So how would you verify calculate the next claims?
It's giving the univariate poly, so you evaluate at R.
We need to modify our.
We can have the same value.
Huh?
Okay.
Is there no way we can get this 0, 6, 24 what we are really
You get 0, 6, 24, yes. But then you need to use 0, 6, 24 to evaluate at 4. Like to get the next claimed sum, you need to evaluate the last round poly that was sent to you
Yes.
at R. Right? So now, what's the last round poly that was sent to you? 0, 6, 24.
Which is an evaluation form.
Evaluation form of a quadratic polynomial.
So
So
you won't be able to use
you'll be able to use your linear interpolate and evaluate to evaluate that R equals 4. So you,
Convert it to
you can convert it to univariate and then evaluate it at.
That means we cannot give our univariate poly this guy straight up. We cannot give it 0, 6, 24.
The verifier.
No, we cannot.
Well, it depends on how you implement your interpolate. Does your interpolate take x's and y's?
Yes.
And then your x's will just be like 0, 1, 2. You can do like value.eta.enumerate to get the x points and then you just interpolate.
So it will work with
Yeah, it's work with this. You just convert it to the form that you interpolate it. Or if you are ambitious, if you are like really ambitious, wait, there are some people that might be ambitious. If you're ambitious, what you could do is, remember how we did the y1 linear interpolate and evaluate? Since you know you're working with GKR, you know that it's only check 0, check 1, and check 2. So what you could do is, the way we did the other one was that we did check 0 times what? Y1 plus check 1 times Y2. So what you could do now is that since it's 3 points, you are going to do check 0, check 1, and check 2.
now we do like bilinear interpolation.
So that check will now be like 2 multiplied by check 1.
No. The check 1 and check 0, check 1, and check 2 will all change because your interpolated set has changed. It's no longer just over 0, 1. It's now over 0, 1, 2. So that your Lagrange, but this is exactly what your Lagrange is kind of like doing already. It's just that what the linear interpolated and evaluate is the same thing as Lagrange. It's just that we made some assumptions that made the formula like much smaller. Because we said that okay, we're always evaluating over 0 and 1. So we simplified it all the way down to something that we can just plug in. But it's still Lagrange.
Lagrange.
X minus 1? No, check 0 is even going to change. You know, it's now over like 0, 1, 2. So check 0 is like x minus 1, x minus 2 over 0 minus 1, 0 minus 2. Do you get? Then you simplify it down. But this is exactly like Lagrange. So Lagrange will just do it. Can we move on? Which one? Check 0, check 1, check 2. The product poly. You don't need to do what? No. The problem is that you can't represent the first one. You don't have anything that represents. No, I'm not representing that. Huh? Because we need to see the correlation between the two. You need to see that if you run it on 6a squared b squared, you get the same Sumcheck messages as running it over the. Should we proceed? Let's proceed. Did you understand? Did you even understand? Did you get to the point where you?
I get to that point. Now, I wanted to start. I'm the main focus of the whole project. Because I was trying to do it here myself.
Okay, so this is 96, right?
Yeah.
Then once you have 96, the verifier will now send R back to the prover.
Yeah.
The prover will now evaluate A at R, right?
To get f of b.
To get f of b. Then he sends it back. Then when he sends it back, verifier, yeah. It's so that you can know what the next. Yeah, the verifier is making calculation. Then send it out to the prover. It doesn't need 96. The prover needs to partially evaluate the initial poly at R. Yeah. No, it's not using 96. You know, the program starts with FABC, then you reduce it to FBC, then you reduce it to FC. The way it does all those reductions is by replacing A with R. So like the verifier is the one that's giving you the R to replace those variables. You get it? So like you have FABC. This is what the prover has initially. The verifier will send him R1. So you will now partially evaluate A as R1 to get F. Then the verifier will send him another one. So this is what the prover is using the R's for. But the verifier uses the R's to get the next claimed sum. Okay, Oracle check.
Yep.
So you check 0, 1, right? 96. Sample last R, 5.
But it doesn't send it back.
It doesn't send it back. That's the last one. So he gets the next claimed sum.
Okay, which will now be the sum that the Oracle check is.
It's supposed to be equal to. Okay. Are we good?
Yeah.
So now we're doing it over product of multilinear polynomials, right? But the way this works is that when you want to evaluate this, you evaluate each one and then multiply the results, right? So this was 0, 0. We evaluated that one, that was 0, 0. All the way down. So we got the same claimed sum, right? Now I wanted to get f of a. To get f of a, we partially evaluate each of them at what? B equals 0. Don't worry. So to get f of a 0, this is a product polynomial, right? So we're going to partially evaluate each of them at b equals 0, right? So that's 2ab. B equals 0 for the first one is what? 0, right? And b equals 0 for the other one is what? So that's like the FA 0. Good? Which is the same thing as 0. So it's like it's just gone. Does it make sense? Then let's focus on FA1. That's what? 2a, right? And 3a. So when you're partially evaluating, you just partially evaluate and then you're done. You don't multiply the things together because they are polynomials, right? And you don't want to get like a quadratic polynomial. So now this is our FA in product poly form. So now that we have this, we want to send it over to the verifier. But then what we do is that we ask it for the degree. The degree is the same thing as the length, right? So the degree is going to be 2. Which makes sense, right? Because if you multiply two of them together,
So that was not what we had before. We have the length of the arrays we go 0, 6, and 24.
the degree, we're getting the degree now.
Okay, I'll change it.
No, the degree is 2.
Yes.
So we'll send 3 points.
Okay.
So the degree is just the length. Makes sense?
Yes.
And now it's what send 3 points. So that's evaluate at 0, 1, and 2. Evaluate at 0, that's what? 0 times 0, right?
Yeah.
Evaluate at 1, that's what?
2 times 3 is 6.
And evaluate at 2, that's what?
4 times 6, 24.
This is what we send over. Makes sense?
Yes.
So we'll send 6 and we'll send this. Verifier doesn't change, right? The verifier is almost doing the same thing, other than the fact that it's doing the same thing. Because this was exactly the same message that the other one sent. The first one we just tried to send. So it's going to what? Do 0 plus 6, right? That's going to be equal to 6. Oracle check is complete. Then, depending on how this 0, 6, 24 was sent to him, you might do like a univariate interpolation, right? So you get 6a squared. Then you're going to evaluate that at R.
Yeah.
You say R equals 4, right? That's what?
96.
Makes sense?
Yes.
Sure?
Yep.
Yes.
Then we send back R equals 4. Cool?
Yes.
Now that we have R equals 4, we now partially evaluate. We want to partially evaluate the product poly at.
R equals to.
Yes, so it's basically like F equals to 4 comma B, right? But this is basically the same thing as, instead of 2AB, it's now be 2 4B.
2 and 3 4
This is the product poly. This is your FB polynomial, but in product form. Make sense?
So we are always going to be returning them
Yes. Whenever you're partially evaluating, it's always going to still be. But when we evaluate, it's going to be like a single point. Cool? So now that we have this, we're supposed to send this over to the verifier, right? But the problem now is that we need to know what the degree is. What's the degree? Huh? 2, right? It depends on the length. So we're supposed to evaluate at 3 points, right? 0, 1, 2. If we evaluate at 0, that'll be what? 0 times 0, right? If we evaluate at 1, that'll be what? Is this correct? And evaluate at 2, that'll be what? This is what we had before. Thank you. There's also multiplication. I was like, what's going on here? So 8 times 12 is what? 96, right? So this from 0 times 0, this one is from 8 times 12, and this one is from 16 times 24. What's 16 times 24? Let there be evidence. And that's exactly the same thing that we got earlier, right?
I don't know what happened to that.
What we did was that we evaluated, this is the product poly after we partially evaluate A equals 4. So now what we're supposed to do is that we're supposed to send this poly to the verifier. So we get the degree. Degree is 2. That means that we need to evaluate at 3 points. 0, 1, 2. So evaluating it at 0 is essentially evaluating each one at 0, then multiplying the results. That's 0 times 0. Evaluating at 1 is like 8 and 12, right? Multiply the results. Evaluate at 2, that's 16 and 24. Multiply the results. Do you get? And that's exactly the same message we sent initially. So this shows that you can run Sumcheck over either fully multiplying it or still leaving it as products. Does this make sense? That's a 10-minute design. Okay? So you have your product poly, you have your multilinear poly already. What does Sumcheck need your multilinear poly to implement? It needs the partial evaluation, right? It needs evaluate, right? What else? That's all. So what you need also is like you need a polynomial that has something like this, right? You're going to call this polynomial your product poly. Now this product poly is going to have a collection of multilinear polynomials. All of them are multilinears, right? So it's kind of like having like a vec of like multilinear 1, multilinear 2, multilinear n, right? Now, if you wanted to evaluate this polynomial, what would you do? Yeah, I want to evaluate polynomial.
And you just evaluate each of the multilinear because each of the multilinear already have evaluate on
Yes. So you just loop over all the things that you hold and call evaluate on them with the same input. Then multiply everything together. That's the result of evaluation of a product poly. Now, what if you wanted to partially evaluate? Does that make sense? What if you wanted to partially evaluate this?
Partially evaluate
each of them.
and you keep them to
Exactly. So you map you iterate over each of them, and then you partially evaluate each of them with exactly the same input. And then you return a vec that is also the same length. You won't multiply them together, even though you are defeating the purpose. So let's say you had like a vec of f of AB, then q of AB, and then d of AB, right? If you want to partially evaluate at, let's say, a equals something, what you are going to return now is like still a vec, that's still the product poly, but it's going to be f of what? We're partially evaluating a. This is your product poly, partially evaluated. Make sense? But now, something will change in your sum check, right? How it sends. So what you do once you are done with implementing the product poly, you need to now implement sum check that can work with product poly, right? So now your sum check is going to take the claimed sum and the product poly, and then it's going to return a sum check proof that should look exactly like, not exactly, but yeah. Yeah, you could create a new sum check, or you could modify your old one. It depends on you. Normal multilinear, but a single multilinear is a product poly with just one element in the vector. You get. So if you want to represent one multilinear poly as a product poly, it's just a vec of one multilinear poly, because it's not going to multiply anything. Yeah, so it's still alright. So if you want to scrap your, but you still do one more change. But it's fine to just do this. But that one is not. It's not too complicated. We'll do that one tomorrow. We'll have time.
Sorry.
Okay. So you know how to do partial evaluate, and you know how to do evaluate for your product poly, right? But then sum check now, before you can send the round poly, it needs to know the degree
for something.
for sum check. Now you're working over product poly. It's no longer guaranteed that your round poly is going to be a straight line, right? So you need to know what the degree of your product poly is. So this means that you need to also implement something called degree or max degree, but let's call it degree.
What will you use a mark to do? What will some check do?
So when the prover has generated the round poly, you know how it does that now? It skips the first variable and it sums the rest of them over the Boolean hypercube. So once it has gotten that round poly, it needs to send it over to the transcript and also put it in the proof.
And
Put it in the proof. You know, your subject proof is a vec of round polys
yes.
and the initial sum.
Yes.
So you need to put that in the proof.
Yes.
So it will be a tuple of as many elements as is needed. In GKR, it's always going to be 3, right? Because it's always going to be quadratic. So you do the degree. The degree will tell you how many points you need to evaluate that round poly at. Does that make sense? Like regular round poly, degree is always 1. So you need to evaluate at 2 points. That's why your round poly has always been 2 points. But now, it's most likely going to be degree 2. But your code should be able to work for any, yeah. But if it's degree 2 now, you're going to be sending 3 points in your round poly. So round poly is basically just like a vec of f.
You are sending vague here, but in your example you were sending what was it? The very poly, right?
Which way? Wait.
So we go down. Yes. You said 6 and 0624.
6 is the initial claim.
They are and 0624
Is the first round poly.
First.
Yeah.
But we now, that's what you did. But what we expect to do is to use the product poly, not
No.
064.
No, when you're sending to the verifier, you're sending a univariate story
Same in the
or a vec of three field elements.
not the product poly.
No, the product poly will have already been like, you will have skipped the first variable
Okay.
and you will have summed the rest over the Boolean hypercube, right? So your product poly will now be a product poly in just one variable.
Okay. Okay.
Let's say you had f of, your product poly was in ABC, right? And you had, let's say, 3 polynomials in your vec. All of them are also in ABC, right? So when you're running Sumcheck, you would skip A and then you sum BC over the Boolean hypercube.
Yeah.
When you do that for all the individual ones, they'll all be FA.
Okay.
So now, that's what you're supposed to try and send over to the verifier, right?
That's what I'm saying.
But you now get the degree.
Mm-hmm.
The degree in this case is 3, right? And so you have to evaluate at 4 points. So you call product poly the evaluate at 0, 1, 2, 3, which will now give you this.
Yes.
Yes. So you store the evaluations in an array, and this will be the,
Yes, which we use in the transcript.
which is what you send to the transcript.
But what I'm saying is, when we are actually sending the polynomial, when we're saying the proof now, when we're saying the proof to the verifier, it's not possible we send the product polynomial.
That's like you want to save yourself stress of like evaluating and then interpolating and all
Yeah,
that.
but I think it's possible to just send the product polynomial, right?
Yeah, you
To
could.
the verifier.
You could. You could. You could. You could. So it's like that's why you also put it in transcript.
Yeah.
So you have it to bytes for the
Not,
product poly.
not necessarily. Is it necessary to put that in? The verifier will run. Okay. I mean, the verifier will have to run the value of A on all of them in the transcript.
No, you no, all the round polys, you're putting them in the transcript.
Yeah.
Like every time you provide the answer round poly, you put it in the transcript. Yeah. So you guys should just attempt it, attempt the product poly, then attempt the modified sum check. Then tomorrow, so this is what you guys can do now as part of GKR. You have the pieces to do to combine these two into just one poly, right? So this will be WI plus 1 B C, right? Then you have the pieces to represent right? Right? This is where we started from. Okay?
Yeah, that's best.
This is where it started from, right?
Yeah.
Now you have something that can merge these two into one. So it will be add I, right? You know how to do this. You should know how to do this. How to merge these two into this, and how to merge those two into this. That's the blow up thing that Francis was talking about. The element wise.
Yeah.
Pen and paper wise.
You do. So wait. Now these two, you know, A will have already been partially evaluated with some R, right? So this is technically the same thing as right? Does it make sense? You sure? Does it make sense why there's no A here? You know there's going to be like Wi of A is supposed to be equal to the sum. That A has already been chosen. So that means the A here will already be partially evaluated. So that means there's no A here and there's no A here. Make sense?
But in minus one put the A like at the bottom.
Yeah, you can put the A. Yeah, I won't do that. So now we have two polynomials that are multilinear and are multiplied by each other, right? So rather than multiplying it fully to get a quadratic polynomial, you can represent these two as a product poly. So the vec will contain this and this,
Plus another product.
then another product poly. So you have product that has like the add and then the W add BC, right? Then plus another product, then you have the mul, then W add BC.
W mod.
Sorry. So you know how to get to this point.
With pen and paper.
You have the tools to get to this point. Somewhere shuffling. So what you now want, the end goal is like, you know how to run some check on this pen and paper, right? On the product poly, you know how to run some check. On another product poly, you also know how to run some check. But then for GKR, you need to be able to run some check on both of them simultaneously. So tomorrow, that's what we're going to cover. Like how to run some check on a vec of product polys.
Is that the alpha beta for
That's not even the alpha beta for.
Wait, we haven't done that.
We did alpha beta in the morning.
Hey, that's what you said.
Yeah, but it's not here. This one is just like you run a sum check and then you get two new sum checks. How do you even run the first sum check? And that's where we are right now. So after we're done with this, we're now going to get two new sum checks. Then use the alpha beta to merge it. Then you get something that looks like this again. Then you now do the product poly stuff again, and then you just continue like that. Yeah.
So like, how many lines of code will you do?
It might not be that long.
Go relax.